Today we are going to solve smoothing spline using linear algebra, but in function space, because last time we have built all the necessary tools to translate all the major linear algebra results into the L2 space. So this time we'll see how we can apply that on our smoothing spline, and we'll treat the derivatives like their matrices, and the sampling process like their operators, and we'll just derive the normal equation just like the ridge regression problem. And towards the end, we'll also see the kernel ridge regression was actually hiding inside this problem the whole time. Okay, so let's start. And we are starting with the one-dimensional smoothing spline problem. And here is the objective that we talked about before. So we have the sum of residual square as the first term, and then we have the penalty term, the smoothness penalty term as the second term. And our goal is to find the function f that minimizes this objective function. Now I'm just going to write this functional in a little different form to match with the inner product of our L2 space. Okay, so here we'll have j, the functional of f equals to y minus t operate on f of x, y minus t operate on f of x. So first norm will be a finite norm plus lambda. We can write the second one as the L2 norm. So I can write it as L of f, inner product with L of f. Okay, so the second one is going to be taking place in the L2 norm, in the L2 space. All right, so here, let me just clearly define what does these operators mean, right? So first we have the T operator, right? So T is called the data operator. And I should also specify the dimension of this problem, right? So the y is a finite dimension, right? So that lives in Rn, and then the function f, and the function f actually don't live in the L2 space. It lives in this space H. Let's call it that. So this T operator needs to map from the function space H into Rn, right? So that's this operator, the data operator. And so you can think of this as a kind of a sampling operator, right? So T of f, T act on f, just gonna give us the finite vector, right? At our evaluation point, right? fx1, fx2, all the way to fxn, right? So that's the T operator here. Right, so it's a map that takes that's kind of sample at fixed data point for the function f, right? So that's what t is. Okay, now let's define the adjoint operator t star. So remember, we can define the t star in this way that the inner product between g and t act on f in Rn equals to t star act on function g inner product with f. It takes place in the space of H. So that means t star maps the finite vector in Rn to function space H. So what is the form of the T star? So the easiest way we can think about it is that it just behaves like a sum of delta functions, right? So it's going to be sum of gi times delta xi, right? So why does this form make sense? Well, formally, if we write down the integral formula of the right-hand side, then we have the right-hand side equals to the integral of summation I gi delta xi times f of x dx. Then we can just pull out the summation and the constant, summation I gi, then you have the integral of delta xi times fx dx. So using the property of the delta function, that equals to summation of I, gi, and then fxi equals to g and tf in Rn, right? This is just the left-hand side. Okay, now we define the data operator T. Let's take a look at the operator L in the penalty term. So L is just gonna be the second derivative operator. So L, let me just use a different color. The L is gonna be the second derivative operator that maps from uh, function space H to L2. Okay, now let's find out what is the operator of L star, the adjoint operator. So that's gonna map from L2 to H, right? And then we can use the same formula here that function G inner product with L act on F. This takes place in L2 equals to L star act on G inner product with F in H. Now let's just find out what is L star operator. Let's write out the integral formula for this. We'll have G x times the second derivative. I'm just going to write in the second derivative in a little different way. I'm just going to write f prime prime of x dx. Then we can apply the integral by parts formula here, right? Remember the integral by parts formula? We have u dv equals to uv minus the integral of v du. So here we can just ignore this term. So that is given by the boundary condition. So if we ignore that term, we'll have minus g prime of x, f prime of x dx. Then we can apply the integral by parts formula again. That gave us the integral of g prime prime of x, f of x dx. This indicates that the L star is also the second derivative operator. Okay, good. Now we have defined all the operators and redefined the problem of smoothing spline in function space. Let's consider how to solve this problem. If we want to find the minimizer for this functional, we're just going to apply variational calculus on it. And the next thing that we did this time is that we written down everything in terms of the dot product or inner product, right? So that's, this is, all of these become linear operations, right? We can almost treat it like they're matrices. So this variational calculus is going to be very different from the time we did last time. And because we can directly operate on this inner products. So let me show you how we can do it. So here I'm remember that we can define the functional derivative in this way that we want to set this functional derivative equals to 0, right? So we're gonna have limit as epsilon goes to 0, and then 1 over epsilon. The first term is gonna give us we're just gonna perturb the function f with epsilon h, and it's gonna be t f plus epsilon h y minus t f plus epsilon h minus that's going to be the first term. And then we have the second term, epsilon lambda, the LF plus epsilon H minus the inner product. I should say this is L2 norm. This is Rn. Because we have the inner product in all of this, right? That means all the operations we are doing here are linear, right? So we can rewrite these things, and for example, the first term become becomes y minus tf, and then we have minus t epsilon th, right? And then that's gonna have we're gonna have the inner product with y minus tf minus epsilon th, right? And then we can kind of just distribute things, right? And then we'll have four terms out of this, right? And then the only term is gonna survive are just the terms with one epsilon in it, right? So and the first term cancels, right? You see that this term when you multiply the first terms of the inner product together, that's gonna cancel with this term here, right? Okay, and here for the simplicity, I'm not gonna write out the term that's being cancelled, right? So you have epsilon 1 over epsilon, and then have minus I think minus 2 uh, y minus tf inner product with th, and this should be an epsilon here, right? And then we have the second order term epsilon square th th. That's the first term. And all of these two norms are Rn, right? These are finite norm for the first term. And then the second term, we have the epsilon over lambda, and then because the derivative operator is also linear, right? So that means these two, the inner product is going to cancel with that, right? And I'm not going to write that as well. So that's going to be what we'll have is epsilon 2 epsilon inner product of L on F with L on H, right? Plus epsilon square L on H, right? So these two are L2 norms, right? This equals to minus 2 times the inner product between y minus tf, th, Rn plus 2 lambda LF LH inner product on L2 space. Okay, so now we can use the adjoint operator to bring the T and L operator to the other side. Okay, so recall that our adjoint operator T star is gonna map from Rn to H, and then L star is gonna map L2 to H. Okay, so we can apply that. This gives us minus 2 times T star y minus Tf H plus 2 lambda L star Lf and H on space H. Okay, this is very nice. That means we can merge these two terms, right? Since the inner product happened in the same place, in the same space. So remember that also equals to 0, right? So we can cancel all the 2, in fact. Then we'll have T star T F minus T star Y plus lambda L star L F inner product with H in the space of H, right? So that equals to 0, and it must hold for all function H of X. Okay, so that means the first term here, right? The first term must equal to 0. This term must equal to 0. So this is the only way we can make this inner product equal to 0 for all function H. So this is just going to give us a normal equation. And let me just write that out clearly. Just scroll this down. Okay. So we'll have T star T plus lambda L star L act on F equals to T star Y. This is a normal equation. And you see this equation actually resembles a lot like our ridge regression problem, which we will connect that in a second. But we'll see here that the interesting thing is our operator is a derivative operator. So that means this normal equation is a differential equation, in fact. That is an ODE. Now, let's just write it out, the exact form for this ODE to see what it looks like. So let me let me just rearrange the term a little bit. So we can do this. In fact, we can write it out as lambda times L star L act on F equals to T star, then Y minus TF. Okay, now let's just plug stuff in. Okay, so this L operator is the second derivative. L star is also the second derivative. Then we have the T star. Let me just write it out this way. So this is, I'm just going to write the word sum of delta. And so it behaves like a sum of delta. We shouldn't take that too literally because these are operators. So now we have lambda times, we apply the second derivative twice on the function f. So that means we get a fourth derivative on f of x that equals to the summation of delta function, delta x minus xi times y minus, so tf is just going to give us a finite vectors, right? So have the yi minus f of xi. Okay, so that is the form of this ODE when we plug in all the operators. You see this form is actually very familiar, right? Yes, this is the exact same differential equation as we derived the smoothing spline during the variational calculus in the previous video. So this is an ODE that is exactly like the thing we derived before. And we shouldn't be very surprised about this, right? Because we are doing the same type of because we are solving the same variational calculus problem, but using a slightly different equation, right? Here we are playing with the inner product and the linear algebra, but before we just apply the Euler-Lagrange equation, the variational calculus directly. That should lead us to the same results. And so here we just see the same thing pops up, right? It is the same differential equation. But this is not our main goal today, okay? So I should say that our main goal today is to use the operators using the linear algebra on function space to look at the ridge regression. So I should write that out clearly that our goal today is to use linear algebra to derive the kernel trick. The kernel trick. This kernel trick derivation is going to be very general. It not just applies to the smoothing span problem, but applies to the kernel ridge regression problem in general. That takes place in the Hilbert space. So the smoothing span is just a special case of that. And from this derivation here, right, from this entire derivation we just did, you already see the structure is very general. We didn't use the fact that L is a derivative, second derivative operator up to this point, right? And we just plug in the second derivative operators here to show this normal equation is the same as ODE we derived before. But up to this point, we didn't care about which operator is the L operator, really. Okay, so for the next part of the video, we're just gonna look at this normal equation here in particular, and to see if we can use the same SVD derivation to get a kernel trick from it. Okay, so here for this problem, right? So actually the tricky part is that we have this L star L in between, right? And to just gain some intuition of this problem, we're just gonna look at the finite version of it, right? We're gonna look at the finite parallel problem for this, right? And let me just write it out, right? So the finite version, and that's where we can just apply our linear algebra on it, right? It's gonna have this for it's the objective is gonna look like this form, right? So this is very similar to the ridge regression, except we have this L matrix to penalize on beta, right? So if we just expanding this out, that's gonna give us beta transpose lambda times beta transpose L beta. Right, so this actually have a interpretation of the graph regularization in it, right? Because we are kind of putting weight on beta using this matrix L transpose L in between, right? So that's gonna be the finite version of this problem, right? And then if we just solve this and do the derivative, that's we're gonna end up with this normal equation in the end, right? So it's gonna be x transpose x plus lambda uh, L transpose L times beta equals to x transpose y, right? So that's going to be the normal equation on it. For this problem, actually, if we do a change of variable, this form is going to be a lot nicer. So consider this, right? Consider a change of variable. And then we're just going to define u equals to L beta. Then we can also define x tilde equals to xl inverse, right? And this requires the matrix L to be invertible. So we can apply this change of variable, and then we'll have this. You can rewrite this into y minus lx tilde u two norm plus uh, the two norm of u, right? So that is this become a ridge regression problem, right? So this is just our ridge regression problem. And then we can apply the same method that we did, and then write out the kernel form for this problem. And for the sake of time, I'm just gonna write out all the results here without deriving the same thing again. Okay, so here let's just quickly go over the kernel trick derived using SVD. That's gonna give us a lot of intuition. We can basically copy the form to the function space if we do it right. So for this problem, here is the normal equation we're gonna get, right? For the ridge regression problem. And remember in the previous video that we applied the SVD, the singular value decomposition on the matrix x tilde. We can also define the kernel matrix as x tilde transpose, right? So that has an eigen decomposition form for the matrix K here. Okay, then we basically just plug in the SVD decomposition for the matrices, and that's the result we have in the end. And here we also want to write out the scalar form for this for the same result, right? For the same vector y hat, right? So that's because that is more applicable for the function space, since we cannot directly play with operators like we are playing matrices, like we are in finite space, right? So this form is going to be more useful, the scalar form, but you can check they are the same. And then we can write out this formula as a kernel trick as k times k plus lambda I inverse y, right? So that means we don't really need x tilde. We only need the matrix K to express y hat. And then we end up calling this whole part here as vector C, right? That means y hat can be predicted as K times C. And then for the vector C, we can also expand it out into a scalar form. It's a scalar times the basis vector. So I think here the basis vector should be ui instead of vi. Let me write that out clearly. So this should be ui, and then we have the basis. That's going to be the basis vector, right? And then we have a scalar, right? Now I think we're ready. We can go back to the normal equation for the operators and to see how we can prove the kernel trick using the SVD formula for operators. Okay, now let's go back to the L2 space to look at our problem. So we started with this functional JF, and then our penalty term has this operator L in it, right? So that's why in our normal equation, we have this L star L operator on F. But now let's see if we can apply the change of variable to get rid of that. The problem here is that L operator is not invertible. And our L is a second derivative, right? It's a second derivative is not invertible. Well, okay, so let me just give you a very easy example. So suppose we have a function x squared, right? So our function, let's call this h of x equals to x squared, right? So L act on h is gonna give us 1, right? So that's, I believe, is a second derivative. But if we do the inverse, right? If we want to do L inverse LH, right? And so that means we are taking that means the L inverse is an antiderivative. So we should find the integral of that. And that's gonna give us some free variables, right? It's gonna be x squared plus ax plus b, right? We have these terms in the back. So this is why we say L is not invertible, right? Because we have those extra terms. And to get around this problem, to avoid this problem, I just define the change of variable in a little different way so that we don't call it L inverse. We apply the change of variable, and then we define g equals to LF, right? So g is a function in L2 space, right? So g equals to LF. There's no problem of that. But instead of doing this x tilde equals to XL inverse, let's just define the operator um, in this way such that SG equals to TF, X down F. And so see here that if you apply this, if you plug in G equals to LF, and then S is kind of like the SLT operator, then L inverse, right? But except that we are not doing except that we avoided the inverse for this operator, right? So now we can rewrite this problem, right? So we have the functional as J of G equals to uh, y minus S act on G, y minus S act on G. This is Rn plus lambda G, the norm of G in L2, right? So after this change of variable, our normal equation is going to look like the ridge regression, right? We'll have S star S minus plus lambda I act on G equals to S star act on Y, right? Also, that's the normal equation have the parallel form with the ridge regression in finite space, right? And this is a problem we're going to solve next. Okay, now let's derive the kernel trick using the singular value decomposition, the SVD for function space. And remember that our SVD formula for function space has this, right? So of function space. So you have S act on eigenfunction, a singular function Vi of x equals to sigma I ui of x. And then we also have S star act on ui of x equals to sigma I Vi of x. And now we can apply it on the function g here. Oh, and another important thing is that I goes from 1 to n. And the reason is that because this S operator kind of maps the function into n-dimensional vector, right? So that's kind of like the rank of this operator S star S, right? And so that's why we only have like n independent components, right? And I should also say that ui of x lives in Rn, right? So that's going to be an n-dimensional vector, and then vi of x are functions, right? That lives in L2, right? But there's only n number of functions. So that's kind of like the rank of this operator. you can just apply this SVD on our function g. So here we also want to make a decomposition of the function g, right? You can write it out as the summation of all the singular vectors, sorry, singular functions vi of x times coefficient ci. So ci is a parameter that we want to know, right? These are the unknown parameters. Let's just apply the operator on it to see what happens. So we're gonna have s star s act on g plus the left-hand side plus lambda g. Because we are in this SVD form, so we can write it out in this way, and then summation, and then have ci times s act on vi of x, right? We can move this thing inside. And then using the SVD property, that's going to give us ui of x times sigma I. And so that equals to s star summation I equals from 1 to n ci sigma I ui of x. Then we can move this thing inside as well. And that gives us summation ci sigma I square and then vi of x. Okay, so that is the left-hand side. We have, oh, I forgot the lambda g in the end, right? And now we can expand this as well, right? And then we have the lambda ci vi of x, right? Then we can merge these two together. We have the ci and sigma I square plus lambda vi of x. So that's left-hand side. So one thing I also want to say here is that in linear algebra, we can just invert this matrix, right? We take the inverse of this, go to the other side. But now we are living in function space. We should be extra careful in here. And the inverse of the operator is not so it's not as easy as matrices because in function space as n goes to infinity, the eigenvalues, singular values are all going to zero. So we should be extra careful about taking the inverse, to just make things safe. I just avoid doing that. So now let's take a look at the right-hand side. So right-hand side is going to give us write out the vector y in terms of the in terms of the singular vectors, right? So y we can write it out as the dot product between y and ui times ui, right? We also need to summation, right? So y are just n-dimensional vector. We can expand it in this way, right? And then as we can do it for any vectors in Rn, right? And then we can apply S star on y. That gives us and that's gonna give us summation y ui dot product, and then we have the S star act on ui, right? S star act on ui is gonna give us sigma I vi of x. Okay, now we can make these two equal to each other, right? So we have the equation of left hand side equals to right hand side, and that's gonna give us ci times sigma I square plus lambda equals to the inner product of yi ui times sigma I. So that means ci equals to equals to y and ui's dot products times sigma I over sigma I square plus lambda. Okay, now we are getting very close. And to compare with the form here, Let's see. Okay, I don't think they are the same C, right? Let's just compare y hat instead, because I don't think this Ci here means are the components in this vector C. And then let me just move this in a little bit to the side. Okay, I'm just gonna clean up the space a little bit. Okay, now using the coefficient Ci, I'm just writing out the function g here as the coefficient times the eigenfunction vi of x. And then to obtain the y hat, so that's gonna be the our predicted value, our fitted value at the evaluation point from y1 to yn. So that's going to equals to the is operator on g, on function g. And we already derived the formula. So we have the sum here, and then we can use is operator on each eigenfunction vi, and that's going to give us ui of x, right? So let's just write it out. So you have summation, I go from 1 to n, and then y ui sigma I and then sigma I square plus lambda, and then s act on vi of x. So that's going to give us sigma I ui, right? We'll have summation I goes from 1 to n, and then y ui sigma I square plus lambda ui. Right, so this is exactly the equation as the uh, as this one, right? As here, right? The equation we have for the y hat. This equals to k times c, right? And okay, I think here I copied the equation wrong. This is this c. This should be ui in here. Here it should be ui. That's can matches the dimension, right? Because remember, c lives in the n-dimensional space, right? The coefficient has n dimension, and our ui lives in Rn, right? It cannot be vi. Vi is infinite dimension. So to obtain c, we can just take the k inverse times y hat. I'm not afraid to take the inverse here because k is a finite full rank matrix, right? I'm not afraid to take the rank, and then if you just plug in the algebra, you'll see that these two equations are the same, right? It's going to be the same as a finite version of the same equation. Okay, so now I think we have successfully proved the kernel trick. Let's do a summary of this. Okay, so for the summary, remember that the first step we did is that we written down this regression problem in terms of the inner product. We have y minus tf, right? In terms of the inner product and the operators, and y minus tf. This is the norm of Rn plus lambda L of f, and the norm of L operate on F on L2 space. So that is the problem setup we did. And then the next thing is that we obtain the normal equation using variational calculus, right? So we use variational calculus. And that gives us the normal equation. But here, a very interesting thing happened is that we didn't actually use the integral formula for the L2 norm. This step is completely general. That means that if we have a linear operator of the inner product, this normal equation is going to hold. It can be derived because we didn't use the integral formula. Okay, so we can see that the entire derivation here, right? We actually derived everything using the inner product, the property of the inner product, and that property is not specific to the L2 space. It can work in any Hilbert space as long as the inner product is properly defined. So here's the punchline, right? So this is can be generalized into Hilbert space. It's generalizable to Hilbert space as long as we have a properly defined inner product for this. So after that, remember what we did is that we have written down the equation in this form that we have the y minus sg and then y minus sg. That's going to be a Rn, right? The plus the lambda of the inner product between G and G. That's in L2 space. So the other interesting thing is that the operator L is completely general. We didn't make any assumption about L, right? We didn't use the fact that we are dealing with smoothing spline problem, so L has to be second derivative operator. We didn't use that at all in our derivation. So so remember that for this we obtain the normal equation as this S star S plus lambda I G equals to S star Y. So in this normal equation, we didn't actually care about which operator we used as the L operator. So in the end, we derived that Y hat equals to K times C, right? So that's the kernel trick. And we derived this without using the explicit formula for the L2 norm or the operator L, right? So all of this means that there's a more general formula for kernel ridge regression. So for the kernel ridge regression, this is y minus tf, and this is on Rn plus lambda times the Hilbert norm, right? So that's going to be the general solution for the kernel ridge regression. And then from here, we can obtain the normal equation as well as the kernel formula, right, for this general ridge regression problem. And the Hilbert norm, right? This is in many cases L operate on F on the L2 norm, right? So that can be a good way to generate the Hilbert norm. But just the important thing is that this equation here is completely general, and then we can obtain the same kernel formula for this problem, not specific to the smoothing spot. And for the next time, we are going to look at this kernel ridge regression problem, the general problem of the kernel ridge regression. Hopefully, in this video as well as the last video, we just sort of see this general formula coming towards our way because we have the same linear algebra structure underpinning this whole time, right? And the fact that we can generalize it once again into the Hilbert space without even specifying the explicit norm for the inner product.